Our vocabulary notes video for today is going to cover in Class 80. This is part 4 of Standard 18. We're going to look at segments of chords, secants, and tangents today. And so to start us off, we're going to look actually at two triangles that are formed by two chords that intersect inside the circle at point E. So the first triangle we want to focus on is triangle AEB, and the other triangle is triangle CED. And we're trying to think back to some previous standards that we've covered to see if we can come up with something that's true for these two triangles. And so the first thing that comes to mind for me is, well, maybe they're congruent. I see some vertical angles here in the middle that I could mark as congruent, back from one of our first semester standards. But one pair of congruent angles is not enough to make triangles congruent. I don't see any marks on segments. And if they're not connected to the center of the circle, these segments aren't congruent because they're radii. So I think the segments are going to be a dead end, which makes me eliminate the option of congruent triangles because I know I'm going to have at least some kind of segment information to use side, 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 or side, angle, side, HL, angle, side, angle, or angle, angle, side. So instead, let's look at maybe these angles up here at the top. So if I look at angle A, that looks like one of my inscribed angles from Standard 17, and it travels out and intersects the circle at point B and D. So the intercepted arc is right here, in between B and D. If I look at angle C, it's another inscribed angle with a vertex on the circle that intercepts that same exact arc. And so we learned that if they both intercept that same arc, that means they're both half of the same measure. They are congruent to each other. So even though I can't say that the whole triangles are congruent, I now have two pairs of angles inside the triangles that are congruent. Back at the beginning of first semester, we learned about angle, angle, similarity. And so these triangles are similar. Angle, angle, similarity makes them similar. Now, it has been a while since we've talked about similar triangles, and so as a reminder, when triangles are similar, corresponding angles are congruent, but corresponding sides are proportional. And so if I look at segment AE, that's in between the star and the arc angle, so that would correspond to segment CE in the other triangle. That ratio has to be equal to the ratio of any other pair of corresponding sides. So I come back to this first triangle. I'm going to focus on segment BE down here. That's going to be connected to the angle that's not marked and the arc in the middle. So that would correspond to side DE in this other shape. And so what I can do is I can write a proportion for which segments are equal to each other. We used to put information in for these segment lengths, and then we could cross multiply to solve problems. And that's actually where our first theorem comes from today. It's called the segments of chords theorem, and that's exactly what we just used in our proportion. AE and CE, BE and DE are all segments of these two chords that we started out with at the beginning of the problem. So if two chords intersect inside a circle, that's describing where point E is located, then the product means multiplication, the product of the segments of one chord is going to equal the product of the segments of the second. Now what we wrote does not look like a product yet, but remember, we can cross multiply. So we can take AE and multiply it by DE, and then that cross product is equal to our other cross product, CE multiplied by BE. So rather than always setting up our problems based on similar triangles, we can jump straight to this multiplication if we want to. We are going to continue on the back side of in Class 80. If you would go ahead and flip the page. And in these two situations, we're going to investigate something similar to the segments of Chords' theorem, but this time it will be the segments of Secant's theorem, and then our last one will be the segments of secants and tangents theorem. And so we're going to investigate again a couple of triangles. Triangle EAD is the first one we're asked to focus on. So from E to A is already connected, but we need to connect that back down to D. I'm going to do that with a dashed line. And then triangle EBC is the other one. So E is already connected to B, but I'm going to connect that then to point C to finish out that one. And so if we're thinking about these triangles, which are a little bit trickier to focus on than the ones on the front side, I noticed right away that they both involved point E, and that angle E is actually used in the very same way in both triangles. So going back in time, we would have said that angle E is congruent to itself by the reflexive property. And now automatically we're up to one pair of congruent angles. The last time, we ended up proving that these triangles were similar by angle-angle similarity. So is it possible for us to get a second pair of angles congruent? I think the key is going to be up here at A and then down here at B. Those look like another set of inscribed angles. This angle CAD intercepts arc CD, so that angle A would be half of CD. And angle B does exactly the same thing. It intercepts that same arc, so it would be half of that same number. So we would be able to say that these are angle A and B are congruent because of that inscribed angles theorem from Standard 17. So again, we end up with triangles that are similar by angle-angle similarity. So if we're looking at the segments that were already on the picture, so not the ones that we dotted in, but the ones that were already there when these secants were drawn in, it looks like EC is going to be one of those segments. So in this bottom triangle, EC goes from the marked angle out to the circle, and it looks like out of these three sides, it's the shortest one. So if I'm looking at this triangle, EDA, that's going to match up with ED. If I go back to triangle ECB, it looks like another side that was there would have to go all the way from E out to B, because the third side from C to B is the one that's dashed in there. So I already used EC on the top of the first ratio, so I'm going to use EB on the top of the second ratio. And that in the bottom triangle looks like it's the longest side. It travels in between our two marked angles. So that's going to correspond to this segment here, that longest side in the second triangle in between our two marked angles. So segment EA. So again, we're going to be able to cross multiply, and in this case we're going to end up with EC multiplied by EA, and then our other cross product will be ED multiplied by EB. Now let's look at what those segments are actually doing in our picture. EC is what I would call an outside segment from that common intersection point to where it hits the circle, the secant the first time. EA is this whole entire segment. So these are on the same secant, but it's taking the outside of that secant times the whole secant. If we look at the second part from the other cross product, the same exact thing happens. We've got the outside part of that secant, and that outside part is getting multiplied by EB, which again is that whole secant segment. So those two segments are also on the same secant. So if you don't want to set up your similar triangles in problems by dashing in extra segments and thinking about what corresponds in the triangles, this can be another way for you to use the segment of Secant's theorem. There is one more situation dealing with these triangles. So this time we're looking at triangle ABD. So ABD, that's kind of weird, but let's go ahead and connect B to D. So this little outside triangle. And then triangle ADC, so I need to connect D to C, would be my other one. So again, like before, I'm noticing that angle A this time is used in both triangles, so that's congruent to itself by reflexive property. And then I noticed that there is this arc stuck here inside of this small triangle. And so it's been a while, but if we look at vertex D on the circle, this is a tangent chord angle. And so this angle right here would be half of arc BD. At the same time though, if I travel back from arc BD over to this inscribed angle, that would also be half of arc BD. So even though this part of angle D is a tangent chord angle, and this angle C up here is an inscribed angle, because they're both half of that same arc, they're going to be congruent to each other. And so one more time, third time today, we have triangles that are similar by angle-angle similarity. So using everything but the dashed segments that I added in, let's start with AB. AB in the small triangle is connected to that congruent angle and then an unmarked obtuse angle. Looks like it's bigger than 90 degrees if we just use looks to help us out. In this big triangle, I have two segments connected to that angle A like they need to be, but this one here is the one that corresponds to AB. It's the shortest side of that big triangle, just like AB is the shortest side in the smaller triangle. So AB corresponds to AD. You can kind of see that in the way these triangles are named as well. If we come back to the small triangle, the other solid side is AD, so that's going to go on top. And then AD is in between my two marked angles. So in my bigger triangle, that would be AC, in between those two marked angles. Cross multiply one more time. So this cross product is unique. AD is going to get multiplied by itself. And then the other cross product is going to be AB times AC. So if we just investigate really quickly to see what's happening, AD is our tangent segment. It intersects the circle at D and then doesn't intersect the circle again. That's getting used twice. So that outside tangent segment is getting multiplied by itself. Those are the tangent segments, both of them. And then over in our secant segment, something similar to over here is happening. AB is that outside segment, and then AC is that whole segment. And just like before, these are on the same secant. So in this one, the tangent gets multiplied by itself, and then the outside part of the secant gets multiplied by the whole secant. We could also have written this as AD squared, since AD is multiplied by itself. So sometimes you'll see this theorem written in terms of squaring the tangent, and then that being equal to the outside part of the secant times the whole secant. All right, that was a little bit longer than normal, but thanks for hanging in there. Bring those vocabulary notes back with you to class, and we will do examples to apply the ideas.